Previous session, we discussed about optical filters, that is fiber Bragg filters and tunable filters, etc. Now we are going to discuss about OADM or optical add drop multiplexer or add drop multiplexer. So you can see in the figure that is a multiplexer combines or multiplexes several lower bandwidth streams of data into a single beam of light. An add drop multiplexer is also has a capability to add more or one or more lower bandwidth signal to an existing high bandwidth data stream. That is important. Okay, an add drop multiplexer has a capability to add one or more lower bandwidth signal to an existing high band data stream. So you can see in the figure that is an option that is to add or drop to an existing wavelength. That is one fiber for wavelength. There are some existing bandwidth, existing wavelength. Along with that, we can add one or more different wavelength to that our drop. So at the same time, they can extract or drop other low bandwidth signals, removing them from the stream and redirecting them to some other network. But you can see this in detail. The function of an optical add or drop or OADM or drop multiplexer is to insert or add or extract or drop. So either we can insert, that means add, or extract from that existing, that is drop, one or more selected wavelengths at a designated point on the optical network. So figure shows a simple OADM configuration that has a 4 input and 4 output. You can see in the figure 1, 2, 3, 4, 4 input ports, and there are some output ports. And here the add and drop functions are controlled by a MEMS based miniature mirrors that are activated selectively to connect the desired fiber path. You can see a mirror MEMS based miniature mirrors. You can see that they are activated selectively to connect the desired fiber paths. So these are the important part in this add or drop. When no mirrors are activated, each incoming channel is passes through the switch to the output port. So each incoming signal is correspondingly passed through switch to the output. So incoming signal can be dropped from the traffic flow by activating the appropriate mirror pair. So by activating the appropriate mirror pair, we can add or drop. So drop that a particular wavelength. So, for example, to have the signal carried on wavelength lambda 3 entering the port 3. So from the you can see in the figure there is a port 3. Let us take that the lambda 3 wavelength is fed into the port 3. So this lambda 3 entering port 3 is dropped to port 2D. So you can see in the port 2D by reflecting from that mirror, this wavelength lambda 3 is reflected through the port 2D. It is not fed to the output ports. That signal is dropped here. So it is dropped. So same way we can add another signal in the lower, the bottom portion of the figure. You can see that port 2A in the port, when an optical signal is dropped, another path is established simultaneously, allowing a new signal to be added from the port 2A to the traffic flow. That is when we are dropping a signal, that is we are dropping that wavelength of lambda 3 through the port 3 by from using that mirror, and that lambda 3 is output through the port 2D. So it is diverted to another path. So at the same time, there occur another part, another option, another path, that is to take or add or input, add a particular wavelength. So in the port 2A, we can add a wavelength that is to that wavelength is equal to that mirror, and by using the reflection, use the reflection of that mirror, that signal is directed to the output. So in here, a particular wavelength the signal comes through the port 3 is dropped, and another signal that is fed to the port 2A is added. That is actually add drop mechanism or add drop multiplexing. Okay, there are many variations on optical add drop device configuration depending on the switching technologies used. However, in each case, the operation is independent of wavelength, data rate, and signal format. Okay, and then let's see the comparison of wavelength division multiplexing versus dense wavelength division multiplexing. I think this term I mentioned earlier, that is dense wavelength division multiplexing, in the previous session. I think you know that the term dense, the density or dense, and you can expect what will be the difference. Coarse WDM has a wider channel spacing. That is, it has a wider channel spacing, 20 nanometers. It's a lot cost. If you are discussing, if you're going to the dense WDM, that is dense WDM has a dense channel spacing. That is, spacing is very less, more number of channels. The dense channel spacing 0.8 nanometer, whereas in the coarse WDM the spacing is 20 nanometer. Whereas in the case of dense WDM, that is channel spacing is zero point 0.8 nanometer. That is dense, which allows simultaneous transmission of 16 plus wavelength that are high capacity. It can allow more number of channels simultaneously. That means spacing is very less. That is actually the dense wavelength division multiplexing. First wavelength division multiplexing network is used just two wavelength. That is only 1310 nanometer and 1550 nanometer. So today's DWDM or dense wavelength division multiplexing systems that are utilizes 16, 32, 64, 128 or more wavelengths in the 1550 nanometer window. Okay, in case of first WDM network, only the just two wavelengths only were here. Today's DWDM system they can utilize 16, 32, 64, 128 or more. There is more number of wavelength that are dense in channel spacing. Okay, so dense wavelength division multiplexing (DWDM) is a data transmission technology having very large capacity and efficiency. Having very large capacity and efficiency. So multiple data channels of the optical signals are assigned the different wavelengths and are multiplexed onto one fiber. DWDM system consists of the transmitters, multiplexers, optical amplifiers, and demultiplexers. DWDM used a single mode fiber to carry multiple light waves of the different frequencies. In DWDM systems that overcome the effects of dispersion and attenuation, channel spacing of 100 gigahertz is used. The channel spacing is about zero point 0.4 nanometer or zero point 0.8 nanometer or 1.6 nanometer, the corresponding to 50 gigahertz or 100 gigahertz or 200 gigahertz. Okay, you can see a DWDM system, dense wavelength division multiplexing system in the speaker. That is, there are different channels, the transmitters having different signals, video, audio, text, data. There will be different type of signals, and they having the different wavelength. So, lambda one, lambda two, lambda three, lambda. These channels having the different wavelength signals through these transmitters. We have these signals are fed to a dense WDM multiplexer, more number of channels, so less spacing, and that's why we are using a dense WDM multiplexer, dense wavelength division multiplexing. These N channels are N is to 1, that is multiplexed into a single channel, that is to that fiber having these different wavelength lambda 1 plus lambda 2 plus lambda 3 etc. to lambda n. So these different wavelengths are combined to a particular channel, and this channel is used as a optical fiber. And along this optical fiber, as I mentioned in the previous module, I think all of you know the optical amplifiers. So we are placing the optical amplifiers on the particular distance through that is inline amplifier, that is in the transmission line, that is in optical fiber path. And after that, this fiber this fiber path fiber is fed to a DWDM demultiplexer. So due to this DWDM demultiplexer, these signals are distributed. It's distributed to the different wavelengths. So these combined signals are combined with a different wavelength. The signals combined with a different wavelengths are distributed to this corresponding wavelengths, and these corresponding wavelength signals are put to the corresponding receivers, receiver 1, 2, 3, etc., receiver again, and that is put to the data output. That is actually the dense WDA multiplexer. It is similar to the WDA, just as similar to the normal coarse WDM system. The difference is nothing but that the more number of channels and the dense that means dense, the spacing is very less.